In this video, we're going to learn how to use the fprintf function in C. So the fprintf function allows us to output a string to an output stream. The output stream is typically a file, but it could be something else like standard output. Fprintf works like printf in the sense that one of the arguments is going to be a format string, and that format string may contain one or more format specifiers. And for each format specifier, we're going to have to supply at least one additional argument to fprintf. Let's go over how to use fprintf. First, we'll create a file pointer variable to allow us to access a file. Then we'll open the file. We'll say file is equal to fopen, file.txt, and then w. So fopen is going to open the file called file.txt. And this w here is going to open the file in write mode. And we're going to store the file pointer that fopen returns into file here. Now, if fopen fails, it's going to return null. So we can check for that. We'll say here, if file is equal to null, we know something's gone wrong in the opening of the file. And we'll print out an error message. We'll say error opening file. And then we're going to return 1 as well. We're going to return 1 instead of returning 0, because returning 1 is a signal to the shell, to the terminal, that something went wrong in the execution of our program. Now, when we open a file in write mode, the file is going to be made blank. So every time we run this program and we write content to the file, it's like the file is going to be starting off again as a blank file. Next, we'll try to use fprintf to write some content to the file. The first thing I'm going to write is actually a special character, new line. I'll say fprintf file, and then \n. So fprintf, as its first argument, accepts an output stream. In this case, the file we just opened. The second argument here is the format string. And the format string in this case is a special character \n. That means new line. So it's going to output a single new line character to the file. When we're done working with the file, we'll want to close it. We'll say fclose file, and that will close our access to the file. Let's compile our program and try it out. So we'll compile it, and then we'll run it, and then we'll examine the file.txt contents. And we see right now, all we have is this new line. That's what the \n is. The \n represents a new line. And so all we get here is this blank new line. Let's try some other things now. We'll try fprintf file. This time I'll say \t, then abc, then \n. So \n will again be a new line. abc will be the characters abc. \t is another special character, and \t is the tab character. So we'll recompile our program. We'll run it again, and we'll check out our file now. And now we see that we get that first line there with the empty new line there. But then we get this tab here, this set of spaces before ABC, and then the additional new line. So the tab character is presented as this series of spaces, like if we hit tab in a text document. But the tab character itself is technically only a single character in the actual file itself, just so you know. It's not like by writing the tab character to the file, we wrote a bunch of spaces to the file. Now we'll try to use the format specifiers. So format specifiers look like this. That's the official breakdown of their format. I'll go over a bunch of these different options, but basically there's flags, width, precision, length, and then the specifier itself that we can use when using format specifiers. I'll also post a link to a breakdown of all the detailed options we've got when using format specifiers. So here I'll say int I is equal to 5, and then fprintf file %d \n. Then I'll give this additional argument I here. So %d is a format specifier, and it's basically saying expect an int. An int value is going to be supplied, and we supply that additional int value here as an additional argument to fprintf. Now fprintf is going to take that integer here, it's going to put it into the string where this %d is, where the format specifier is. So if we save this now and recompile our program and then run it, and we check with the file, we now get 5 output. So the format specifier %d allows us to output an int value. We can also output a character with the format specifier %c. I'll say here car c is equal to d. Then we'll say fprintf file %c \n, and we'll have c here. We can save this, recompile, and run it, and check out the file, and there's d. We can use %f for both floats and doubles. So we could say here float f is equal to 2.125, and then fprintf file %f \n f, and we'll say double d is equal to 9.82, and then fprintf file %f \n and d. And if we save this, recompile, run it, and check out the file, there are those two real numbers there. We can also output strings using %s. So I could say car string is equal to ABC. Then we could say fprintf file %s \n string. And now we can output the string ABC. So we'll recompile, and we'll run it, and we'll check out the file, and there's a string ABC. So when I use fprintf, I like to end my format string with \n. So that way each time I call fprintf, I'm writing a line to a file. We don't have to do that though. We could say here fprintf, and we'll say file %d space, and it'll have 1 here. Then we'll say fprintf file %d space, and I'll put 2 here. And then fprintf file %d, now I'll have a \n, then I'll have 3 here. What this is going to do is output the number 1 followed by a space, but there's no \n here. So the next time fprintf runs, it's going to continue to output on the same line as before. And we'll get the number 2 output, and then the number 3. And then we'll do a \n to complete that line. So we could save this, recompile our program, run it, and check out our file. And we have 1, 2, 3 on the same line. So it's \n that's going to effectively complete the line by printing out a new line. And we don't have to output it when we create our format string. I just do that as sort of a habit. Let's go over some of the options we've got here. So there's a number of options in terms of flags and width and precision that are going to affect how things are output. Let's try these out to see how they work. We'll say here fprintf file and then %4d \n and then 22. So it looks like we're using the d specifier for an int, and we are. But this time we have this 4 here. 4 is going to specify a field width. So that way 22 is going to be output into a field of width 4 characters. We'll save this and we'll give it a try. We'll compile, we'll run it, we'll check out the file, and we have 22 here, but it's output into this field of width 4 characters. And you can see the 4 characters there. We have these 2 leading space characters there. So we can output numbers and other things into fields with a certain width. We can also left align them within those fields. So for example, we could say fprintf file, and this time we'll say %-4d. I'll put this arrow here with end, and then \n, and then we'll have 22, and we'll save that. And if we give this a try, we'll compile, run it, and check out the file. Now we see that 22 is also output into this field of width 4 characters, because we can see end here, and we can see those additional 2 characters here. but this time the value is output in the field left aligned. We can also output a value into a field with leading zeros. So we could say fprintf file, and we'll say %0 for d \n, and again we'll put 22. This time leading zeros will be placed into the field. So we'll compile, we'll run it, and if we check out this last output here, we have these two leading zeros. We can also put the sign of a number, positive or negative. Now by default, we do get the minus sign with negative numbers. So for example, if we have fprintf file, and then %d \n, and I output 1 and -1. So here we have two format specifiers. So I'm supplying two additional arguments to fprintf, 1 and -1. If we save this, compile, run it, and check out the file, negative numbers automatically will have the sign output. We can force the sign to be output though, even if the number is positive. We'll need to use the plus symbol. So we'll say fprintf file. This time we'll say %+d, %+d \n, and we'll have 1 and -1. If we save this, compile, run it, and check out the file, now we've forced the output of the sign, even if it's a positive number. Now, normally when we output a real number, the number might be output with more decimal digits of precision than is really needed. So here if we say fprintf file, and then %f \n, and we output 1.2345. If we save this, compile it, run it, and check out the file, in the file we have 1.2345 and then two more zeros of precision. We can limit the amount of decimal digits in our output by using dot and then specifying a number, or also providing an argument by using star. So for example, if we say fprintf file and then %.2f \n and then 1.2345, we're specifying two decimal digits of precision. So if we save this here, compile, run it, and check out the file, now the number is output with two decimal digits. We could also use star and supply an additional argument for the decimal digits of precision. So for example, we could say fprintf file, and we'll say %.star f \n. Now we actually need to supply two arguments. One that sort of takes the place of star here and supplies the decimal digits of output precision that we want. So we'll say 1 here for 1 decimal digit of output precision. Then we also supply the floating point number itself. So we'll say 1.2345. So we can save this, compile our program, run it, and check out the file. And now we get the number output with a single digit of decimal precision. We could also say here int digits is equal to 3. We could then call fprintf with file, and we'll say %.star f \n, and we could say digits here, and then 1.2345. So the argument for this star here, for the decimal digits of precision, could also be determined by a variable. So our program could programmatically determine the number of decimal digits of precision at runtime by setting this variable to whatever we want it to be. We can save this, compile it, run it, and verify that it works. Now we get 3 decimal digits of precision. We can also output numbers in different formats. So for example, we could say here, fprintf file, and we'll say %e \n, and then 2.4123. This will give us a scientific notation output. So if we save this, recompile and run it, and check out the file, we'll see that number output using scientific notation. We can also output pointer values, where a pointer is really just a memory address. So we could say fprintf file %p \n, and we'll say and digits. The and operator will give us the memory address of digits, and we're going to output that here. So we'll save this, compile it, run it, and check out the file. And there we see the memory address of digits. We could also output different kinds of numbers like unsigned long numbers, for example. So we could say here, unsigned long UL is equal to, and we'll make a very large number here. So a very large number there. And then we'll output the number. We'll say fprintf file %lu \n, and we'll put UL here, and we'll save this. We'll recompile, run it, and check out the file. And there's our very large number. So if there's a number in C, we can output it with fprintf somehow. It's a matter of knowing the right format specifier to use. We could also put data in an array using fprintf. We'd likely want to use a loop though to help us loop through the elements of the array. So for example, let's say we have this float array of results. And we'll have 5 elements in our array. Maybe these are results of some computation that a program does. We could then make a loop to loop through this array. So we'll say for int I is equal to 0, I is less than 5, I++. And I is going to go from 0 by 1 up until, but not including 5. So it's going to take on the values of 0, 1, 2, 3, and 4. So we can use I to output each element in our array. We'll say fprintf file, and we'll say %f \n, and then results at index I. And if we save this, compile, run it, and check out our file, there's our array elements there. Now we could output these using the same format specifier arguments we've used before. So we could say 0, 7, .2 here. And if we save this, compile it, run it, and check it out now, now we have leading zeros. That's what the 0 does. The .2 will give us 2 decimal digits of precision, and we have that here. And the 7 here will output into a field of width 7. And that's exactly what we have here. We have 4, 5, 6, 7. Now we could also output the data from a 2D array as well. So for example, let's say double data 3, 3. So we'll make a 2D array with 3 columns and 3 rows. And we'll say 1.1, 1.2, 1.3, 2.1, 2.2, and 2.3, and then 3.1, 3.2, and 3.3. There's different ways we could tackle this problem. One thing we could do is make a loop to go through each row in the 2D array. And with our fprintf function call, we could have 3 format specifiers to output each value in each column within that row. So for example, we could say for int I is equal to 0, I is less than 3, I++. And we're going to use I to go through each row in this 2D array. So we'll say fprintf file, and we'll say %.1f, 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 \n. So we're going to output each floating point number with 1 decimal digit of precision. And we'll say data at index I 0, data at index I 1, and data at index I 2. And what we're doing here is accessing each column's value within each row as given by I here. So we have one loop to go through each row in the array. And our format string has these 3 format specifiers to output the value at each column within each row. So we could save this, recompile, run it, and check out our file. And now we have this nice 2D grid of output. We could also use a loop within a loop. So for example, we could have one loop to go through each row in our 2D array, and another loop to go through each column in our 2D array to output the value at each column within each row. So for example, we could say for int I is equal to 0, I is less than 3, I plus plus. And then for int j is equal to 0, j is less than 3, j plus plus. So now this counter variable I is going to be our row counter variable. The counter variable j is going to be our column counter variable. And what we'll do is print out to the file %.1f, and we'll output data at index I and index j. And to an extent, what we have here is sort of a unrolled version of what this loop is doing here. What this loop is doing here is for each row index I, it's going to output the value for each column from 0 to 2. This time using the counter variable j to go from 0 to 2. Now after we output each column's value, we'll also output a new line. We'll say fprintf file and then \n for a new line to end that line. I'm also going to output a couple new lines in between these printouts, just to separate them a little bit. So I'll put 2 new lines here to separate these 2 2D grids of numbers that we're going to output. So we'll save this, recompile, run it, and check out our file. And there's our second 2D grid of numbers. And it's identical to the first here. We've just done it in a bit of a different way. Now, when we output 2D grids of things, whether the numbers or something else, we might want to output it into a bit of a table format, where we use specific field widths when outputting the data into our table to give us the column effect of having columns of data. We could also output headings for our table. Let's go over an example of that. I'm going to have 3 columns of output of field width 5. So here I'll say fprintf file, and I'll put these column headings into 3 fields of width 5. And I'm also going to left align the fields. So we'll say %-5s, %-5s, and %-5s \n. And we'll call each one of these column headings D1, D2, and D3. So what I'm doing here is outputting 3 strings, D1, D2, and D3, using these format specifiers here. And they're all the same, %-5s. So put the string into a left-aligned field of width 5. This is going to be our column headings. Now what I'm going to do is every time I output the data in this 2D grid here, I'm going to output each value into a field of width 5. That's going to give us the effect of columns. Before I do that, I'm going to output a row of stars to separate the column headings from the data. I'll use a loop to help with that too. So I'll say here for int I is equal to 0, I is less than 15, I++, and I'm going to print out 15 stars. I'll say fprintf file and then star. So because I have 3 columns, each of width 5, I'm going to output 15 stars to give a line separating the column headings from the table data. Then I'll have an fprintf to the file with a / and new line here to finish this line of stars here. And then when we output each value here, we'll output the value into a field of width 5 as well. So because we're outputting everything into a field of width 5, we're going to have the effect of 3 columns of field width 5. I'll also left align each value in its field as well, just to make the table look a little bit nicer as well. So we'll save this. We'll compile our program again, run it, and check out the file. And now we have the effect of this nice table here, where each column has this width of 5 characters here. So we can do this sort of thing as well with fprintf to give nicely formatted output. We can also output some special characters as well, like the / character and the double quote character. So I'm going to output a couple new lines here, just so we can see what I'm talking about a bit better. So right now we're using the / character here to output special characters like the new line and the tab. What if I actually want to output /? To do that, I can just use 2 backslashes. So I could say fprintf file, and I'll say / like that. This will output a single /. We can save this, recompile, run it, and check out our file. And there's that single /. We could also output a double quote by using a / as well. So we'll say fprintf file, and then / double quote. And this will output a double quote. So normally the double quote has been used to terminate the end of this string literal here. But here we're using it as an actual output character by putting this special / in front of it. We call this the escape character. We can save this, recompile, run it, and check out our file. And now we've output a double quote as well. So fprintf can also be used to write to standard output. In other words, what is by default the terminal or the shell here. We have to use the special standard output stream stdout to do that. So we could say here fprintf stdout, and then we'll have test followed by a \n. So by using stdout, what's going to happen in this case is that instead of writing to the file, we're going to write to standard output. In other words, the terminal, the shell here. And we're going to output the string test followed by a new line. So we could save this, recompile, and run it. And now we get test output there. So fprintf does have a return value, and the return value is the number of characters written to the output stream. If there's an error, it will return a negative number. So for example, if we said here int result is equal to fprintf file, and we'll say ABC. So there's 3 characters being written to the output stream. If we print out the result, it should be 3. We'll say result %d\n, and we'll output result. If we save this, compile, and run it, we get a result of 3. So this is how we can use fprintf to print out formatted strings to output streams in C. Check out portfoliocourses.com, where we'll help you build a portfolio that will impress employers, including courses to help you develop C programming projects.